Hi everyone, I'm Sukanya Joshi. I'm an AI ML solutions consultant, and today I'm going to be talking to you about MLOps in Snowflake. All right, let's start with the development aspect. So this includes preparing the data, training, and tuning the models. With notebooks on container runtime, you as ML developers can seamlessly use SQL, Snowpark APIs, and feature store APIs to prepare data and engineer features for model training. From there, you're free to leverage any open source ML packages to train your models, and then use container runtime APIs to scale that training across large datasets, all within the Snowflake environment. Feature Store is our native product that enables data scientists and ML engineers author and define features, use Snowflake to maintain and update those features with new source data, and serve the features for use in training or inference pipelines. There are four main benefits of using the Feature Store in your ML workloads. First, Snowflake keeps your features fresh and updated automatically. You do not have to worry about orchestrating your feature pipelines. Second, there are easy-to-use APIs to define all the common types of features that you need, both in SQL or in Python. Third, Feature Store handles all the point-in-time correct joining so that you can retrieve features that are consistent with your desired timestamp. And lastly, Feature Store makes it super easy to find and reuse your existing features. So in terms of ML container runtime for notebooks, what is it? It is a fully managed container environment built for machine learning with support for both CPUs and GPUs. It comes with pre-installed open source ML packages, allows you to add your own, and is optimized for loading data directly from Snowflake. Plus, it supports distributed learning APIs, all accessible right within your Snowflake notebooks. So why use it? It gives you the flexibility to run ML workloads at scale without moving data outside of Snowflake. You can hit the ground running with pre-installed ML libraries or install any custom packages that you need with pip. How do you use it? So you just have to create a notebook, select on runtime, run on container, and then use your desired CPU or GPU image and assign a compute pool. You can define features directly as data frame operations, making the process intuitive and consistent with existing Snowpark workflows. A built-in helper library simplifies common transformations like time window aggregations, and you can specify a refresh frequency to ensure features are automatically updated as new data arrives. With support for metadata such as versions and descriptions, it's also easy for search, manage, and reuse features across teams. In this workflow, you can perform data engineering and preparation by executing both SQL and Python within the same Snowflake notebook. This allows you to work with Snowflake data using either Pandas or Snowpark data frames and take full advantage of Snowpark APIs, UDFs, and stored procedures to transform the data for model training. You can load features directly from the Snowflake Feature Store and enhance your workflows by leveraging any open source libraries like scikit-learn or feature tools for processing and feature engineering. For model training and experimentation, you can use pre-installed open source packages right out of the box, or install additional ones from public or private repositories using pip install. When it comes to scaling, you can accelerate data ingestion with distributed data loading APIs and fully utilize GPU resources through pipeline data loading and training using sharded data connector APIs. Additionally, you can scale model training across multiple GPUs or CPUs with distributed training APIs, enabling efficient large-scale experimentation directly within the Snowflake environment.
For model tuning and promotion to production, we begin with hyperparameter tuning using popular OSS packages like HyperOpt or Optuna. For larger datasets, use Snowflake ML distributed hyperparameter optimization APIs, as well as Bayesian strategy for optimized results. Once tuned, you can promote to production using Git integration in notebooks to push changes made during ML development to a Git repository. You can easily connect to your repo, commit the changes, and push to the production branch when you're ready.
Now we're going to move on to the next step, which is train and validate. So as for ML container runtime for pipelines, we can execute ML training tasks via orchestrators like Airflow. You can use any OSS or Snowflake ML code to create pipeline components, and this can be done in any IDE of your choice. There's no need for data movement as all the compute is pushed down to Snowflake. Scaling is effortless, whether you need CPUs or GPUs to handle your workloads, and the solution is highly optimized for machine learning, leveraging distributed data loading, training, and hyperparameter tuning, all while extending popular open source libraries for even better performance. As for the Compose training pipeline, we use Container Runtime as the single platform for end-to-end ML development. You can compose ML pipelines and work entirely within your preferred IDE, such as VS Code. The notebook content is modularized into separate PY files, each containing ML runtime compatible code, including any OSS packages and APIs for distributed data loading, training, and hyperparameter optimization. For configuration of CI/CD, set up GitHub Actions or an equivalent to trigger pipeline execution on commits from development to production branches. And you can leverage internal package repositories like JFrog to create a Python environment that enables smooth execution of ML pipelines. As for CI/CD, you can execute training pipelines directly from VS Code or any IDE, iterating on each code component with ML runtime function pushed down until production ready. You can trigger the pipeline execution using orchestration tools such as Airflow, Prefect, or Snowflake task graphs. You can also use existing task monitoring capabilities in orchestrators like Airflow with the ability to fetch Snowflake logs remotely for tracking. Our next portion of the ML workflow is management and governance. The Snowflake Model Registry helps you unify all aspects of model governance and management in Snowflake. Before Model Registry, many customers were writing ad hoc UDFs by hand to create model inference functions in Snowflake. Model Registry provides several advantages over this. First, it is a unified catalog of all your models in one place, including custom models and Cortex fine-tuned LLM models. It supports rich metadata, metrics, tags, and versioning. Also, models in the registry are inference ready and automatically deployed and available for inference from SQL or Python in the warehouse. Users do not have to do anything additional. Like everything else in Snowflake, you get all the governance benefits through the model objects, such as fine-grained role-based access control, the ability to manage lifecycle of models through development to production, and there is also built-in end-to-end lineage from which you can see the source features and data sets that the model is using. Finally, Model Registry simplifies collaboration and provides ways for securely sharing models within and across accounts. So Snowflake's Model Registry is a single unified catalog to securely manage, govern, and use ML models. It offers built-in support for popular frameworks like Snowflake ML, XGBoost, scikit-learn, and more. You can also bring in any Hugging Face model or pipeline and use the custom model API to log any arbitrary model type along with its code. It even supports the table function models, which are useful for logging partition models. Additionally, you can specify pip or conda dependencies to ensure your model environment is fully reproducible. On the right, you can see a sample script on how to log the model as well as use the custom model API. In terms of storing relevant model metadata, the Snowflake Model Registry has capabilities for model descriptions and comments, versioning, setting the default version, saving model metrics, applying model tags and aliases, and storing arbitrary KV pair metadata. On the right, you can see some sample scripts on how you can implement this in the registry. In terms of model lifecycle management, Snowflake provides clear role-based access with owner and usage roles. You can use model aliases to indicate different stages of the model lifecycle, apply tags to manage and control which versions are considered live or production, and easily copy or promote models from a development environment to production. You can visualize model lineage directly in the Snowset UI, allowing you to easily trace the flow of data from source to prediction and understand how each component of the model pipeline is connected. You can also securely share models across accounts and regions in Snowflake. As a provider, you export the model and include it in an application package, which is then listed on the Snowflake marketplace. A consumer installs the app and the model object is created directly in their account, allowing them to seamlessly invoke model functions as part of their workflows. Now let's move to the next step of our ML workflow, which is model deployment and serving. All right, so in terms of taking a look at inference from the model registry, What it is a streamlined way to serve models for fast, scalable inference via SQL, Python, or REST API endpoints. Why I use it? It enables distributed inference on both CPU and GPU without needing to write UDFs or manage container infrastructure while supporting any pip installed packages. How to use it? It's very simple. You can simply log your model in the model registry and create an inference service using a single API call. When you log the model in the model registry, Snowflake automatically deploys the necessary UDFs for inference, which can be called from SQL using model predict or Python using model.run. This enables distributed inference on your warehouse nodes. Additionally, Snowflake now supports serving models via Snowpark container services, providing GPU-powered inference and support for any pip-installed packages. Using the Create Service API, Snowflake handles container management and deploys the model service. Once deployed, you can run inference from SQL, Python, or through a REST API endpoint for external applications. On our final part of the ML workflow, we have model observability and monitoring. Monitoring the overall health and performance of your models goes beyond just understanding explainability or feature contributions. Since model-driven decisions can significantly impact your business, it's essential to continuously monitor models in production for performance, data drift, and the quality of incoming data to ensure those decisions remain reliable and trustworthy. Snowflake's ML observability extends the end-to-end operationalization of ML models by enabling automatic tracking of key performance metrics once a model is deployed. If any of your defined thresholds are breached, alerts can be triggered to notify the appropriate team or system, allowing you to take timely action, such as retraining the model or rolling it back. These observability features are easily accessible through the Monitoring tab in the Model Registry UI. All monitor model inferences are stored in Snowflake. All you have to do is write a single SQL command to enable monitoring, and this stores the inferences in a Snowflake table using the source parameter. Or you can even pass it in as a view. It also supports external model inference, and classification and regression models are supported. On the right-hand side, you can see a sample script along with its parameters in terms of how you can create a model monitor. We also have the out-of-box dashboard in the Snowsite UI. This helps access monitoring dashboard for a model version from the model registry. You can also choose the appropriate time range, and the dashboard will reactively aggregate appropriately. You can also compare two model versions if you're running an A/B test. In terms of configuring metrics, that's very flexible as per your use case. There are three different types of metrics that are supported: activity, performance, and drift. Performance metrics are available based on model task, being classification or regression, and these metrics can be changed at any point in time. On the right-hand side, you can see the monitoring settings in the Snowsite UI. You can also set up alerts and notifications on metrics. You can use metric functions to query these monitoring results. You can set up alerts on these functions as per your required granularity. You can also take downstream actions such as retraining a model, starting a data pipeline by using tasks or stored procedures. And you can use Snowflake-supported notification channels such as email, webhooks, Slack, Teams, and PagerDuty. So just taking a step back, we've covered a lot about the end-to-end ML workflow, but in terms of the development, we have a tightly integrated set of features from notebooks to pipelines. So we can easily, using Snowflake notebooks, we can perform any type of transformations, feature engineering, and model validations. We can register this model, extract it into separate PY files, push it into a remote GitHub repository, and also create a CI/CD pipeline with ease. From there onward, we can deploy the model to production. In terms of model deployment itself, we also have tightly integrated set of features to confidently deploy these models to production. So in terms of the model registry, we have model management and governance. This includes model versions, metrics and metadata, and the model lifecycle. Moving on, we could move that into batch serving and online serving. And finally, we have so many features for model monitoring and observability. For example, we have operational monitoring, drift monitoring, accuracy monitoring, as well as features for explainability as well. Thank you so much for listening. We hope you learned a little bit more about MLOps in Snowflake.